Okay, so I think let one or two more people join, then we can start. So where are you right now? You have come back to Guwahati or your hometown? Okay, let me share. Okay, so anyway, I think we can start the class. So today we'll learn about this thing, law of mass action. So this note means this document has been uploaded to Google Classroom already. So you can find it in Google Classroom. And in the last class, we learned about this metal semiconductors and insulators, the difference from Venn diagram, and you can find it from the book also, this Puri and Babbar textbook. Okay. So the next topic we are going to learn is this law of mass action. Okay. So let us go through it. It's just some theoretical thing. Okay, so the law of mass action states that the product of number of electrons in the conduction band and the number of holes in the valence band is a constant at a fixed temperature and is independent of amount of donor and acceptor impurity added. Okay, mathematically it is given as Np equal to Ni square equal to a constant quantity. So what is Ni here? Ni is the intrinsic carrier concentration, and N is the number of electrons in the conduction band, and P is the number of holes in the valence band. Okay. So what is it? Let me read again. The law of mass is that the product of number of electrons in the conduction band and the number of holes in the valence band is constant. Okay. So what are conduction and valence band? Maybe I can draw quickly. So this is suppose the band of a semiconductor. So here we are talking about semiconductors mainly when we are talking about law of mass action. Okay. So this is the valence band. This is conduction band. Okay. So the number of electrons in the conduction band. So conduction band there will be electrons. Okay. So the solid dots are electrons, and here we have holes. in the valence band. Holes are not solid, but like this. The product of number of electrons, number of electrons in the conduction band and the number of holes in the valence band is constant at a fixed temperature as independent of donor and acceptor impurity. Okay, so what are these donor and acceptor impurity? So sometimes you dope your semiconductors. Okay, so semiconductors are like intrinsic semiconductor. What is an intrinsic semiconductor? Intrinsic semiconductor means there is no impurity in the semiconductor. Okay, no impurity. And extrinsic semiconductor means the semiconductor is doped with impurity. Okay, and the doping can be donors or acceptors. I don't know whether you have learned about doping of semiconductors or not, but yeah, that is the thing. Semiconductors, depending on the nature, whether it is very pure semiconductor intrinsic and doped semiconductor extrinsic. Okay. So according to law of mass action, this is the statement, mathematical statement. The number of electrons n, small n represents the number of electrons in the conduction band, this one, and small p represents the number of holes in the valence band, this one. Okay, so this product is a product is a constant. Okay, and the constant means it is actually equal to Ni square. Ni square is equal to constant. Ni stands for intrinsic carrier concentration. Intrinsic means the semiconductor is not doped. It is a pure semiconductor. Okay. So that means, yeah. So that is the thing, and independent of donor and acceptor impurities. So donor and acceptor impurity, like sometimes you dope your semiconductor with other elements like boron, aluminium, gallium, nitrogen, phosphorus, etc. So even if you add those impurities to your semiconductor, they do not affect this particular relation. Okay, this particular relation of multiplication of electrons and protons. Okay, so this is the main statement of law of mass action. Okay, then the law of mass action is applied for both intrinsic and extrinsic semiconductors. Okay, so intrinsic semiconductor, just now I have mentioned that intrinsic semiconductor means there are no impurities, or simply the semiconductor is a pure semiconductor. Okay, without any impurity. Impurity may be donor impurity or acceptor impurity. Okay, and this law of mass action holds good for both extrinsic and intrinsic type of semiconductors. For intrinsic semiconductors, for extrinsic semiconductors, okay, extrinsic means again the semiconductors which have been doped, or in other words, where you have added impurity elements. Okay, those are the extrinsic semiconductors. And why impurity elements are added? So if you just want to know, so impurity elements are doping. Okay, so doping involves addition of impurity elements. So doping is done to change some properties of the semiconductors, like electrical properties, optical properties. Okay, so suppose in an extrinsic semiconductor may not be very good conductor of electricity. Okay, but if you add a little bit of impurity to an intrinsic semiconductor, then it can become very good conductor of electricity. Okay, like optical absorption or optical emission properties may not be very pronounced for intrinsic semiconductors. Okay, but if you add sometimes if you can add impurities to your semiconductor, in that case the electrical properties or optical properties, whatever, that may change significantly. Okay, after doping. Doping means extrinsic semiconductor. Okay, so that is one of the reasons why semiconductors are often doped with impurity elements. Okay, Okay, so this law of mass action holds good for both intrinsic and extrinsic semiconductors. For extrinsic semiconductor, the law of mass action states that the product of majority carriers and minority carriers is constant at fixed temperature and is independent of amount of donor and acceptor impurity added. Okay, this is also same definition as the previous case. The law of mass says that the product of majority carriers, okay, and minority carriers. Majority carrier means in a semiconductor, what are the majority carriers? So electrons or holes, whatever be the majority carrier, okay. Because you see, in an extrinsic semiconductor, okay, I think I have to type a few things. So have you read about doping of semiconductors before in any class? Have you read about doping?
Yes, sir.
Okay, then I think you should be familiar with these things. So extrinsic semiconductor, okay, semiconductor, is the spelling right? Conductor. So they can be of generally two types, so P type and number two N type. So what is P type? P type means holes are the majority carriers. Okay, P type stands for holes. Holes are majority carriers. N type stands for oh, sorry. This annotation was annotation is removed. Okay, I will maybe I will type again. So extrinsic semiconductor N type and number two P type. Okay. In N type, the charge carriers are majority charge carriers are electrons. Okay. N means negative type. P type, the majority charge carriers are the holes. So it depends, like how you dope your semiconductor. Okay. Like if you add things semiconductors like I'm sorry, if you add elements like nitrogen, phosphorus, etc., then an intrinsic semiconductor becomes N type. Okay, of course N type is also an extrinsic type semiconductor, but it will become N type. And if you dope with elements like I think boron, then gallium, I think I'm right. So with those you can get P-type semiconductors. Okay, P-type semiconductors are also extrinsic semiconductors, and in P-type semiconductors, holes are the majority carriers. Okay, unlike electrons in uh, uh, unlike electrons in N-type semiconductors. Okay, so here you see this statement. You check this statement for extrinsic semiconductor. Extrinsic means this type of semiconductors. The law of mass action states that the product of majority carriers and minority carriers is constant at fixed temperature and independent of amount of donor and acceptor impurity added. Okay. Okay, so in later section we will learn about this multiplication terms. So what is the so which quantities are constant you have to multiply and which quantities are constant for this extrinsic semiconductors. Okay. So then law of mass action for N-type semiconductor. So I hope you have understood this statement. Product of majority carrier. Majority carrier means for N-type semiconductors, majority carriers are electrons, and for P-type semiconductors, the majority carriers are holes. Okay. So their product is constant at fixed temperature, just like the previous case we have learned for intrinsic type of semiconductors. And this is also independent of amount of donor and acceptor impurities. Okay. So how much donor and acceptor impurities we have added, it doesn't depend on that. Okay. Okay, so let us learn individually what are the laws of mass action for n-type and p-type semiconductors. The law of mass action for n-type semiconductor is mathematically written as something like this. So Nn Pn equal to Ni square constant. Okay. So be careful about these terms what have been written, mainly these first two terms, Nn Pn. So what is Nn? So see, we are dealing with n-type semiconductor. Again, n-type semiconductor means electrons are majority carriers for this type of extrinsic semiconductor. So for extrinsic semiconductor, okay. So here, so these are the cases of extrinsic semiconductors, okay. Because intrinsic semiconductors there are no n-type or p-type. But yes, for extrinsic semiconductors there are n-types and p-types, okay. Okay, so how you write the law of mass action for n-type semiconductors? The law of mass action for n-type semiconductors is written as Nn Pn equal to Ni square is equal to constant. Okay, so what is Nn? Nn is the number of electrons in n-type semiconductor. Pn, number of electrons in the n-type semiconductor. Oh, sorry, number of holes in the n-type semiconductors. Okay, since the semiconductor is n-type, therefore this in subscript, mainly you check the subscript terms, we have n, n, okay. So don't get confused. So this n, the first n, okay, maybe I have to annotate here. So there are two n terms, don't get confused. So this n stands for electrons, number of electrons. And this n, which is in the subscript, this represents that it is an n-type semiconductor. So don't get confused with this. Okay, so here it is written number of electrons. Electrons means this n, and this n stands for n-type semiconductor. Okay. Similarly, Pn stands for number of holes in the n-type semiconductor. Number of holes. So P stands for the holes. And this small n, or in the subscript n, stands for n-type semiconductor. Okay. So I hope you have understood the law of mass action for n-type semiconductors now. So Nn Pn equal to Ni square. Okay, so don't get confused with two n's. Okay, three n's. There is another n here, but this n stands for like intrinsic carrier concentration. Intrinsic carrier concentration means how many number of charge carriers will be there if the semiconductor was intrinsic. Intrinsic means not doped. It is neither n-type nor p-type, but it is a pure semiconductor. And what will be the concentration of carriers in that case? Okay. Okay, so this is the law of mass action for n-type semiconductors. Okay. So okay, various terms are given here. So I'll remove the annotation and. Okay, so then the electrons are majority carriers. Okay, so in n-type semiconductors, the electrons are majority carriers and holes are the minority carriers. Okay, so we have already discussed about these things. So in n-type semiconductors, electrons are majority carriers and holes are minority carriers. Okay, in n-type semiconductor, as the number of electrons or majority carriers in the conduction band increases, the number of holes in the as the number of holes in the valence band decreases. Okay, so here what is written, The number of electrons in the conduction band increases and the increases. Okay, there should have been a comma actually. The comma is not given here. And the number of holes or minority carriers in the valence band decreases. So since they are like in n-type semiconductors again, electrons are majority carriers and holes are the minority carriers, and therefore electrons are always there in the conduction band. Okay, therefore in n-type semiconductors there will be more electrons in the conduction band and less holes in the valence band. Okay, so that is what you should remember. Maybe I can draw it quickly. Just try to explain by a simple drawing. Okay, I have drawn this 4 holes in the valence band, but I'll try to draw more electrons in the conduction band. Okay, so you see there are more electrons in the conduction band and there are more holes in the, there are less holes in the valence band. So this type of semiconductor is the n-type. Okay, that is what is it, n-type semiconductors. Number of electrons in the conduction band increases, comma, there's no comma here. The number of holes or minority carriers in the valence band decreases. Okay. So that is the thing. So in n-type, the name n stands for negative type semiconductor. Negative type semiconductor means the majority charge carriers are the electrons, and p-type means just the opposite, where majority charge carriers are the holes. Okay, I hope you have understood this. Therefore, the product of electrons, majority and holes, minority, remains constant at fixed temperature. Okay, that is the thing. Here, product of electrons and product of electrons, which are the majority carriers, and product of holes, which are minority carriers, equal to Ni square. Or Ni is constant. Ni square. Ni stands for the intrinsic carrier concentration. It remains constant. Okay, at fixed temperature. Okay, the temperature should be fixed, because if you, why we are writing the, they are writing that temperature, fixed temperature, because if you keep on varying the temperature, then the carrier concentration will keep on changing. Okay, so as you supply more temperature, more number of electrons will be there in the conduction band than the in the conduction band. Okay, therefore you should always keep the temperature fixed, so that there is little variation in the number of electrons in the conduction band. Okay, a little or no variation. Therefore that is why we are writing fixed temperature. Okay, so higher is the, more is the temperature, it will be more difficult. Like if you keep on increasing the temperature, it will be difficult to follow this law of mass action. Okay, because in that case continuously this n and p and those values will be varying. Okay, therefore your temperature should be fixed. Okay, so now just the other way around, opposite way. The opposite way is law of mass action for p-type semiconductors. Earlier it was n-type and now it's p-type. P-type semiconductor means, again, in p-type semiconductors you have more number of holes than electrons. Or in other words, the holes are the majority carriers and electrons are the minority carriers. So how you can write the law of mass action for p-type semiconductors? So Pp Np equal to Ni square is equal to constant. So what is Pp? Number of holes in p-type semiconductor, Np number of electrons in the p-type semiconductor. Okay, so here again these two p terms are there, Pp, Pp. So number of holes in the p-type semiconductor. So this P, big P, this stands for the number of holes. This small p, it stands for p-type semiconductor. That is what is written, pp number of holes in the p-type semiconductor. Okay, np number of electrons in the p-type semiconductor. So this is the term np, and again if you multiply them you have ni square. Okay, Ni is the again intrinsic charge carrier concentration. So this equation is written in the same line, same way as the previous case. Okay, but remember this time we are dealing with p-type semiconductors. In p-type the subscript should be p when you write the law of mass action, and in the n-type the subscript should be n. So other things will remain the same. Okay. Okay, so pp number of holes in the p-type and np number of electrons in the p-type semiconductor. Okay, so in a p-type semiconductor the holes are the majority carriers and electrons are the minority carriers. Okay, so it is very easy to understand, since the like p semiconductor is p-type. P-type means the positive charge, positive type. Okay, positive charge type. In p-type semiconductor there will be more positive charges than negative charges, and the positive charges are the holes. Therefore holes are like majority carriers and electrons are the minority carriers in the p-type semiconductors. Okay, and this is the law of mass action. Okay, so again in p-type semiconductor the number of holes or majority carriers in the valence band increases the number of electrons in the conduction band decreases. Okay, so same but opposite as that type of n-type semiconductor. So here if I draw this diagram, band diagram, p-type semiconductor there will be more holes in the valence band. And there will be fewer number of electrons in the conduction band. Okay, so you can see these are the holes, more holes in the VV, and in the conduction band you have fewer number of electrons. So this is just the opposite of n-type, p-type. So this is just the opposite of n-type semiconductors. In n-type we have more holes in the conduction band. Sorry, more electrons in n-type. There are more electrons in the conduction band and less holes in the valence band. In the p-type we have more holes in the valence band and less number of electrons in the conduction band. Okay, so I hope you have understood the differences between the p-type and n-type semiconductors. Okay, so that is what is written. Therefore the product of holes, majority and electrons remains constant at fixed temperature. Okay, therefore at fixed temperature product of holes and electrons remains constant. Okay, product of holes, majority and electrons remains constant at fixed temperature. That is the, this is the, so the last line means this this equation, the equation for law of mass action. Okay, so yeah, again the temperature has to be fixed, otherwise the carrier concentration means electron and hole concentrations will keep on varying. Okay. Okay, so I think that's all about the law of mass action, and this note is already there in Google Classroom. You can make the note directly from there. I did not get it in the textbook, therefore I have given it to you from some source in internet. Okay. Yeah. Okay, so one topic finished. So let me check what is there next. Holes, band gaps, energy band diagram. Classification of solids. Okay, so have you yet learned band theory of elementary band theory of solids?
Mm, No, sir.
No, not yet. Then
No, sir.
classification of solids. Okay. Okay, solid classification we have done. About bands also we have done more or less. Concept of holes, and then law of mass action. Then insulators and semiconductors is given separately. I don't know what is this mean, insulators and semiconductors. Why it is given separately? Then last topic given is Hall effect in metals and semiconductors. Okay, Hall effect can be done. Hall effect is there everywhere. So can you do Hall effect today? Okay, let me go through the Puri and Babbar book and see how Hall effect is given there. If it is fine, then we can start doing Hall effect today. Hall effect. Let me check the syllabus, please. Okay, Hall effect, it is not there. Oh, law of mass action is there in the Puri and Babbar book in page 212. It is there. Page 212, law of mass action is there in Puri and Babbar book. Okay, so you can also check that. No, Hall effect I am not finding here. Okay, if Hall effect is not there, then I can check another book. I can check another book and there Hall effect should be there. Oh, but wait, Hall effect note I have in some this class. Did I give you Hall effect note already? So MSc third sem. Yeah, maybe I have given them Hall effect notes. Just let me check that. Oh no, just in MSc second semester, not third semester. Second semester, how is it? Yeah, Hall effect in metal and semiconductor. Yeah, I got the Hall effect PDF. Yeah, I got the note which I gave them. Okay, Hall effect. I think I will keep the figure of Hall effect is not here. Hall effect. Is it? Okay, the figure I can show you. So I think when we are doing your practical, I showed you the same figure, your practical and Hall effect. Okay, let me share. Okay, so I hope you can see this Hall effect, and I think I showed you this figure earlier also. Okay, so what is going on? So this is a specimen. Okay, uh, this is a suppose semiconducting sample or any current conducting sample. So what happens? So a current is flowing. So you see I. Okay, this I symbol you see it means a current is flowing like this. Okay. So a current is flowing, it is coming from this side and it is flowing across the length of the sample, this sample, okay. So now what you do, so current is flowing means is the like electrons, okay. So current is its direction of conventional electric current, and conventional electric current is due to the flow of electrons, okay. So all of you know that conventional current flow of electrons. Now what you do, you apply a magnetic field B. Okay, this magnetic field capital B, which is applied perpendicularly to this specimen, okay, to this sample. So what happened? So initially this specimen, this brown color specimen is carrying a current, okay, just you remember that. And then it is carrying a current, but then what you do, you have applied a magnetic field B perpendicular to the specimen, okay. Then what will happen, this magnetic field, because of the presence of magnetic field, there will be a force on the charge carriers, okay. So what this force on the charge carriers will do, Lorentz force to be precise. So this Lorentz force will separate the electrons, okay, from the holes. The negative charges, this minus and negative charges, they will be separated from the positive charges, okay. Why? Simply because of the Lorentz force due to the magnetic field, okay. So Fm you see here magnetic force on the negative charge, and Fe you see electric force from the charge buildup, okay. So therefore the charges are separated from electrons and the holes, and this separation of charges, okay. So due to this separation of charges, a voltage will be developed across the specimen, not along the length of the specimen, but across the width of the specimen, okay. So negative charges on one side, positive charges on one side, and a because of the charge difference on either side, a voltage difference will be generated. Because you know that potential difference, sorry, what is potential difference? This is the amount of work done to take unit positive charge from one point to another. So since the charges are different on this case, and due to this difference of charge, you have to do a work to bring some unit positive charge from this side to this side, or negative charge from this side to the other side, okay. And for that reason, a voltage is developed across the specimen, and this particular voltage is known as the Hall voltage. Okay, so that is how this Hall voltage is generated in the specimen. Okay, so you have already done this practical, so it should be easier for you. So Hall effect, okay, some note is given here, but here a lot of things are given. So okay, this particular case is true for n-type semiconductors. Okay, and if the semiconductor is p-type, in that case holes will be gathered in the left side and electrons will be gathered in the right side. Okay, that is the case of p-type semiconductors. Okay, just the opposite. This is for n-type, this is for p-type. Where depending on whether the semiconductor is n-type or p-type, so these charge carriers will be the charge carriers, be electrons or holes, will be like gathered accordingly. Okay, so these mathematical derivations are not required, as I have seen in your syllabus. Only quality, what is it? Qualitative discussion only, no quantitative discussion is required. So I think we will not go for that numerical things. And the note I will give you from I have already notes written on Hall effect from MSc classes, so that same note I will give to you. Okay, so that you can read it from there. Okay, so maybe I can share the note with you, and then okay, as you can see here, Hall effect in metals and semiconductors. Okay, so what is Hall effect? So Hall effect was discovered in the year 1879 by this E. H. Hall, Edwin Hall, if I remember his name. Edwin E. Hall observed that when an electrical current passes through a sample placed in a magnetic field, a potential proportional to the current and to the magnetic field is developed across the material in a direction perpendicular to both the current and the magnetic field. Okay. Oh yeah, so one more thing is that this potential which will be generated, it will be perpendicular to both the current and the magnetic field. This is also one thing you have to remember here. So this effect is known as Hall effect. So Hall is just after the name of the scientist who worked on it, and is the basis of many practical applications and devices such as magnetic field measurements and position and motion detectors. Okay. Okay, so so maybe I can take you to the same figure which you were seeing earlier. Yeah, I hope you can see this. You see, so this Hall voltage, okay, you have seen the Hall voltage is generated across the ends, okay, across the width of the specimen, and this Hall voltage is perpendicular to the current, okay, and perpendicular to the magnetic field. Maybe I can draw quickly. Okay, so this is the current, okay, this is the magnetic field. The Hall voltage is generated like this. Okay, current, sorry, this is magnetic field, this is current, and this is, suppose I write as VH, Hall voltage. Okay, so this Hall voltage will be proportional, will depend on both the current and magnetic field, and at the same time the Hall voltage will be perpendicular to each one of these. Okay, so all of them are perpendicular to one another. The magnetic field is perpendicular to the current, the Hall voltage is perpendicular to both the current and the magnetic field. Okay, so all this VH, Hall voltage, current and magnetic field, each are perpendicular to one another. I think you can also understand it from this figure. Okay, magnetic field is directly up, so it is perpendicular to the Hall voltage and the current. Okay, and the Hall voltage is developed across the specimen, and it is also perpendicular to the current. Okay. Okay, maybe I can draw this specimen in another way. Okay, this is the current. Okay, and the Hall voltage will be across this specimen, across the width. I may write it as VH. Okay. So perpendicular to the current agent. So that is also one aspect of this Hall voltage. Okay. Anyway, I think I will stop here, and this particular note I will upload to your Google Classroom. So Hall voltage we have learned already what is Hall effect, and there are some applications of Hall effect. So whether like these applications you can see, and Hall effect in metal and semiconductor we will discuss briefly in the next class. Okay. So in one or two more classes maximum, we can finish the syllabus. Okay, this week, next week we can finish the syllabus by January 1st week. Okay.
Yes, sir.
Okay,
Yes, sir.
so I think I am stopping today's class because I have another class from 10 a.m. Okay, and the note on Hall effect I will